Before a website shows you a single pixel, before it reads one header, before your scraper sends anything you would call a request, your client has already introduced itself. That introduction is the TLS handshake, the short negotiation that sets up the encrypted connection every modern site runs on. And it turns out that handshake says a great deal about who is really knocking. Today I want to explain TLS fingerprinting, how a site reads that opening negotiation, and why a lot of automated clients get sorted and blocked before their first real request ever lands. I run proxy infrastructure and production scrapers, so I spend a lot of time on the defending side of this, studying how detection works and why it works. I want to be clear about the frame before I start. This is an explainer of how the mechanism operates, told from the site's point of view, not a guide to defeating anything. The useful thing here is understanding, and as you will see, the durable answer is not disguise. It is a client that is honestly what it says it is, so there is no contradiction to catch in the first place. What the handshake actually is. Start with the basic exchange. When your client connects to an HTTPS site, nothing secret can flow yet, because the encrypted channel does not exist until both sides agree on how to build it. So the client speaks first, in the clear, with a message called the client hello. That message is a shopping list. It says which version of TLS the client supports, which encryption methods it can use, and a set of extra options it would like to negotiate. The server reads that list, picks what it likes, and the secure channel gets built from there. The fields that give a client away. Here is the part that matters. That opening client hello is not one fixed thing that every client sends. The exact contents vary from one piece of software to another. The list of cipher suites, which are the encryption methods on offer. The set of extensions, the little add-on options, the supported groups and signature methods, and, crucially, the order all of those appear in. None of it is secret, none of it is encrypted, and all of it is visible on the very first packet, before a single byte of real content moves. Cipher suites and their order. Take the cipher suites first. A browser like Chrome offers a specific set of them, in a specific order that reflects what its developers decided to prefer. Firefox offers a slightly different set in a different order. A plain scripting library that was written to just get a connection open offers something different again. Often a bare or unusual list, because nobody tuned it to look like a browser. So the mere lineup of encryption methods, in the sequence a client lists them, already starts to describe what kind of software is really on the other end. Extensions add another layer. The extensions do the same thing. These are the optional features a client asks for during the handshake. Things like the server name it wants, which rides along in an extension known as SNI, the protocols it is willing to speak, and how it will handle certain security checks. Real browsers include a characteristic bundle of these, arranged a characteristic way. A generic HTTP client tends to send a much thinner set, or the same features in a telltale different order. Stack the cipher list and the extensions and their ordering together, and you have a surprisingly specific description of a client that never had to reveal its name. Submissions in Tapir. Penguin is a way to talk about these patterns compactly, and that is where JND comes in. JND is a method that takes several of those handshake fields, the TLS version, the cipher list, the extensions, the supported groups, joins them into one string, and hashes it down to a short fingerprint. Two clients that negotiate TLS the same way produce the same JND value. So instead of eyeballing the whole handshake, a site can compute one small ID on the first packet and compare it against known values. A given browser version tends to land on a known fingerprint, and so does a given scripting library. JAV4, the sturdier successor. JAV3 had a weakness. Browsers started randomizing the order of some extensions on purpose, which made the simple hash jump around and lose its meaning. So a newer scheme, JAV4, was designed to be sturdier. Instead of one brittle hash, it builds a more structured fingerprint that stays stable even when parts of the handshake shuffle, and it captures a bit more of the picture. The details are less important than the directions. The fingerprinting got more robust, not less, and the fields it reads are still ones the client hands over freely at the very start. The contradiction the site is looking for. Now the piece that ties it to scraping. A common automated client sets a user agent string that says it is a current browser, because the user agent is just text and you can put anything in it. But that same client negotiates TLS using whatever its underlying library does. And that library was never trying to imitate a browser. So the handshake produces a fingerprint that says generic scripting tool, while the header a moment later says modern Chrome. Those two things do not match. The site is holding a client that claims to be one thing and connects like another, and that disagreement is the whole game. Why the library, not the label, decides the handshake? It helps to see why this is so hard to fake casually. The user agent lives in the request, a line of text your code writes. The TLS handshake is produced far below that, by the encryption library your language and tooling sit on top of. The shape of the client hello comes from that stack, from OpenSSR or whatever equivalent is underneath, not from the string you set. So setting a browser user agent changes the label without changing the behavior. The site is reading the behavior. That is why the contradiction is so reliable. The two signals are generated in different places, and only a real browser naturally makes them agree, sorted before the first request. This is why blocks can happen so early. The Jamia 3 or Jamia 4 value is computable from the client hello, which is the first thing the client sends, before any HTTP request, before headers, before a URL is even seen. An edge network sitting in front of the site can read that fingerprint on the opening packet and decide right there how much to trust the connection. By the time your scraper thinks it is sending its carefully set headers, the sorting may already have happened. The phrase blocked before the first request is not a figure of speech. It is literally the order of events. It costs the site almost nothing. Part of what makes this so widely used is how cheap it is. Every HTTPS client has to do a handshake, no exceptions. So the signal is always there and always in the clear. Computing a fingerprint from it is a tiny bit of work that happens right at the edge on infrastructure that already terminates the encrypted connection anyway. The site is not running an expensive check or challenging the client with a puzzle. It is reading something the client was always going to send, and it gets that read for free on every single connection. A signal that arrives on its own, that no client can decline to give, is exactly the kind a defender loves to build on. Consistency is the real test again. If you have heard me talk about browser fingerprinting, this will sound familiar, because it is the same principle, one layer down. Detection is not really hunting for a single forbidden handshake. It is checking whether the handshake agrees with everything else the client claims. Does the TLS fingerprint match the browser in the user agent? Does it match the headers that follow? A real browser passes this without trying, because one real piece of software generated all of those signals from the same place. An assembled identity has to keep every layer telling the same story, and the layers are produced by different parts of the stack. Some tooling does try to reproduce a browser's exact handshake, and it is worth being honest that this exists. But it is a moving target, not a solved trick. Browsers change their TLS behavior as they update, the fingerprints shift, and an imitation that was perfect a few months ago drifts out of date. Worse, an almost right handshake can itself be a tell, a fingerprint that matches no real browser version cleanly. This is the same arms race you see everywhere in detection. The ground moves under both sides, and anyone promising a permanent match is selling something that expires. What an honest client looks like here. So where does that leave a compliant operator? In a good spot, actually, because the honest path sidesteps the whole problem. If a job genuinely needs a browser, drive a real one. A real browser produces a real browser's handshake, because it is a real browser, no imitation required. If a job does not need a browser, then let the client be honestly what it is, a scripting tool, and identify it as such where the site expects that. And best of all, prefer an official API or data feed when the site offers one, because that front door does not care about your handshake at all. The honest client never creates the contradiction, so there is nothing to catch. The honest limits. Let me be straight about the boundaries, the same way I always am. Nothing here makes a client undetectable, and I would not believe anyone who told you it did. TLS fingerprinting keeps improving. Jar 4 is proof the measuring only gets sharper, and what slips by today can be flagged tomorrow. Matching a handshake is not a durable strategy. It is a treadmill. The durable strategy is not to be in a fight at all. The moment collection leans on pretending to be a browser it is not, or reaches for private data, or ignores what a site clearly asks, it has left the honest lane, whatever the tooling looks like. I run this infrastructure in production, so I study TLS fingerprinting from the defending side because it makes the collection I build more honest and more durable, not because I am trying to slip past anyone. If you want to go deeper, the full written guides, the handshake breakdown, and the compliant patterns are at dataresearchtools.com. Third person and defensive throughout, with no undetectable promises and no bypass how-to. The point is to understand the handshake well enough that you never need to fake one. So to recap, every HTTPS connection opens with a TLS handshake, and that handshake is sent in the clear before any page loads. The cipher list, the extensions and their order describe the client, and methods like jar 3 and jar 4 compress that into a fingerprint a site can read on the first packet. A generic client whose handshake says scripting tool while its user agent says browser has produced a contradiction, and sites sort on exactly that, often before the first request. The honest response is a client that is genuinely what it claims to be, so the contradiction never exists. Subscribe for a new scraping infrastructure breakdown, and I'll see you in the next one.